Teacher Oswald, you are welcome. Take on the floor.
Hello, good morning, everyone.
Good morning.
I welcome everyone for coming to attend this wonderful seminar of chemistry, ordinary level, or what we normally call O level. You're all welcome. Should I get started straight away?
Yes, we can get started.
Okay, thank you so much, Mr. Kakoro, and everyone for being here. First of all, I want to thank Iyaka for giving us this opportunity to share and we discover more about chemistry, in particular about the topic we shall discuss today. I hope everyone got a copy of the questions that we are likely to look at. So allow me share the screen. Okay. Mr. Kakuru, I'm requesting if you can share with everyone the copy of the questions. Thank you. So that we can follow each other. So dear members, today we are going to look at a topic called carbon and its compounds. This topic cuts across. In some schools, it is done in senior 2, third term. In some schools, it is done in first term, senior 3. And in some other schools, it can also be done in senior 4. So it cuts across from senior 1 to senior 4. This topic is about carbon. And like I said, it is covered in ordinary criminal level. It is examinable at the end. And today we are going to follow the old curriculum, the one we've been following, not the new curriculum. So we are going to be following the principles of that curriculum. So I want to first ask, what we people know about carbon and its compounds. You might find that we have members here who have so far covered it. They can share with us. You just raise up your hands or you send a message via the chat box. The members present. Anybody who knows anything about carbon and its compounds, you can help us, share with us the little you know about carbon. I'm going to look through the list and just ambush someone. Yes, Martha. Martha, anything you know about carbon and its compounds? Martha, you've gone off. Okay, so carbon is basically found in period 3, period 2 of the periodic table, and it is also in group 6. We have an answer from Miracle. Miracle says carbon is capable of forming long chains and is capable of isomerism. Thank you, Miracle. That is true. But under this, we shall not go far to isomerism or forming those long chains. Normally, the formation of long chains is covered under organic chemistry. That's when we look at the long chains. This time we just simplify, or we just look at a few things about carbon. So as we wait for more answers, we have some objectives for this lesson or this seminar. First of all, we are saying that by the end of this lesson, you should be able to define allotropy and allotropes. We should also be able to name and describe the structure of diamond and graphite. We are going to see what diamond and graphite are in this case. Also be able to state the properties of diamond and graphite. Also, we can also be able to prove that allotropes of carbon contain solely carbon. What do we mean here? We want to confirm or give a proof as to why we say carbon or why we say diamond or graphite is made up of carbon. So we need to perform a demonstration or perform an experiment to confirm that. You know, in science, we have to confirm everything. We have to be sure 100%. We don't guess around. Then be able to explain the reactions of carbon. Carbon has got different reactions, as we shall discuss if time allows. So at the end of this session, all of us should be able to at least explain a few things, a few reactions of carbon. And then also describe the preparation of carbon dioxide. So when we look at carbon dioxide, is under the oxides of carbon. Mainly carbon has two oxides. It has carbon dioxide and also carbon monoxide, and at times oxalates. So, but for us this time around, we shall look at carbon dioxide. Then we shall also look at other oxides later on. Then also be able to explain chemical and physical properties of carbon dioxide as a gas. So those are the few objectives for our seminar. This topic is a bit longer, and we can't cover it in 1 hour or 2 hours. Otherwise, if we do that, we might miss out some information. So where do we find carbon? As I said, carbon is we are saying that carbon is found in period 2. It is found in period 2 and also in group 4. When we say it is found in group 2, it means that it has 2 energy shells, or what we normally call energy levels. Carbon has atomic number of 6. So if I'm to write its configuration, it would be 2, 2 to 4. So as I said, here in period 2, because of having 2 energy shells. So it has 2 energy shells. Then we are saying it is in group 4 because it has 4 electrons in its outermost energy level. Energy level. Okay. In case you have any questions, please feel free to ask. I'll be able to answer you. Then we're also saying it has atomic number of 6, like I said. It has atomic number of 6, which is here. And can we have anybody to define for us what atomic number is? Anybody who can help us define this word, atomic number, so that we can know the meaning as we proceed? Anybody who can define for us atomic number, so that we can understand what we mean when we talk about atomic number? Anybody? You can either raise up your hands or you can use a chat box. Anybody who knows how to define atomic number or what atomic number is? Okay, Mira, once again, atomic number is the number of protons in the nucleus of an atom. Thank you. Atomic number is the number of protons in the nucleus of an atom. We can add there the nucleus of an atom of an element. Of an element. Thank you, Miracle. Anybody who has got a different definition? Apart from what Miracle has said? Anybody with a different definition of atomic number? Okay. So let's move with what Miracle said. Atomic number is a number of protons present in the nucleus of an atom. When you're defining atomic number, please make sure that you also add the nucleus of an atom. Some of us, when defining that, we just say atomic number is the number of protons, and we stop there. This is wrong. This is wrong. You have to go on and add in the nucleus of an atom, of also an element, because atoms are found in elements. So you have to state all that. Okay, thank you. Once again. Occurrence. When we go to occurrence, we want to see where do we find carbon, or where can we locate carbon? Anybody who knows where we can find carbon? Anybody to share with us where we could find carbon? Anybody who can share with us where we can find carbon? By show of hand or by using the chat box, please, you can share with us. Let's make sure that by the time we end this seminar, all of us at least have given an answer. Okay, Martha says carbon is found in the atmosphere. Martha, thank you. Another person? Another person? Another person? Where do we find carbon? Apart from what Martha said, where else can we find carbon? All right. So we say that carbon occurs in both free states and also in combined states. What do we mean by free states? When we say free states, this is where we find carbon alone. It is just alone. You find that a substance is purely made of carbon. Then when we say combined states, it means that carbon is combined somewhere, maybe in a compound. For example, if I have a compound like carbon dioxide, within carbon dioxide we have this carbon. So here we say that carbon is found in a combined state or in carbon dioxide. Or if I have, let's say, calcium carbonate, here still carbon is found in a free state, rather in a combined state, because it is combined within calcium carbonate. It is within a compound. So there we say it is in a combined state. And then when we go back to free state, that is where it is just alone. We find carbon alone without any other substance. So in combined states, it occurs as a cone. It occurs as a cone. Mineral oils. It also found in carbonates, e.g., that is limestone. Limestone is the same as calcium carbonate, which also doubles as marble. Then we have seashells and all living things. When we talk of living things, we mean animals and also plants. So when we say living things, again, we mean animals. Any animal that you know contains carbon, as we shall see. Then as an element, when we say carbon as an element, this is where we mean in free state. This is where carbon is found in free state. Anybody who can remind us the definition of an element? Anybody to remind us the definition of an element so that we can understand when we say carbon as an element? Anybody? Anybody to remind us what an element is? Anybody to define for us an element? An element, those things were covered in senior 1, senior 2. So we can't say it is done at senior 4 if you are not yet in senior 4. Martha, what is an element? Martha, I'm sure you know this. Martha, what is an element?
An element is a substance that cannot be split up into smaller substances by any chemical means.
Okay, thank you so much, Martha. So that is how we define an element. It can't be split into any simpler substance by any chemical means. In other words, when we say carbon in a free state, it means it can't be split into any other simpler substances. And we say as an element, it occurs in both natural, that is when it is as diamond, and also as graphite, and also synthetic forms. When we say synthetic forms, these are kind of artificial. So in such a case, we have coke, we have charcoal, all of us know charcoal, and also carbon fiber. So there are a few substances where we can find carbon, whether in combined states or in free states. So we move on. If there is any question concerning what we have so far covered, please feel free to ask. Any question to whatever we have covered so far? If there are no questions, let's proceed. Let's look at what we call allotropes of carbon. Allotropes of carbon. If you remember very well, among these objectives, we say that by the end of this lesson, we should be able to define allotropy and allotropes. The word allotropy comes from the word allotropes. So anybody who could be knowing what allotropy means? Anybody who knows what allotropy means? Let's use the available resources. You can use the internet. You can ask the neighbor. Allotropy. What is allotropy? Allotropy. What is allotropy? Anybody to help us? Once again, if you have the answer, you can use the chat box, or you can mute yourself and you talk to us, or you raise up your hand. Allotropy. Okay, let's wait for more answers. Let's look at what I have. Wow, we have an answer. Miracle says allotropy is the existence of an element in more than one physical form. Okay, thank you, Miracle. Once again, she says allotropy is the existence of an element in more than one physical form. So carbon that we are looking at today shows allotropy. It has that power or that ability to show allotropy. In other words, carbon can be in different forms. Martha says is an element that exists in 2 or more different forms. Okay, thank you, Martha, for trying. So let's look at what I have. So you're saying that allotropy is the existence of an element in two or more forms in the same physical state. Existence of an element in two or more forms in the same physical state. In other words, we can have carbon existing in different forms. We can have carbon existing in different forms, but remains carbon. Though it is existing in different forms, but it remains carbon. So like how all of us human beings, we have the same blood, the color is the same, it is red, but we have different skin colors. Some are dark, some are brown, some are chocolate, but all of us have the same blood. So here, the same thing. We can meet different things, but all of them are made of carbon. So how about allotropes? How about allotropes? Remember, we have said allotropy is the existence. Then what about allotropes? How can we define allotropes? These two are connected. These two are connected. If we are able to define allotropy, then we can be able to also define allotropes. So allotropy, we are saying it is the existence. This word is very important, existence of an element. So from allotropy, we can get allotropes. So what are allotropes? You can share with us what are allotropes? What are allotropes? What are allotropes? Anybody to try? So as we wait, let's look at what are allotropes. Okay, an answer has come. Miracle says allotropes are different physical forms of an element in which allotropes are different physical forms of an element which is capable of allotropy. Thank you, Miracle. Martha says allotropes are different forms of elements with the same physical properties but different chemical properties. Okay, thank you for trying. Any other person? Any other person? Like I said, make sure that by the end of this lesson, at least you should give us at least one answer so that we can also add in the records that you gave us an answer on 25th June 2022. So like we said, these are various forms in which elements exist without change in physical state. So these are various. When we say various, we can also put different. We can also put different forms. So if you don't want to use the word various, you can use different. The word different forms. They are the same. So I can always say that allotropes are different forms in which elements exist without change in physical state. And once again, it's not only carbon that undergoes this. It's not only carbon. We have other substances or other elements like sulfur. Sulfur also shows allotropy, but we shall not go into details of sulfur, but also shows. Then from there, let's look at the allotropes of carbon. So allotropes of carbon, we have three. We have diamond, we have graphite, and also amorphous carbon. But what is so unique is that diamond and graphite, these ones we call them crystalline. They call them crystalline allotropes of carbon. So these ones are made of, they are like crystals. They're like crystals. If you ever see the diamond, let's say in the movies or in the pictures, it's like a crystal. The same applies to graphite. But we are going to look at these ones individually and we get to understand them more.
Hello, Teacher Oswald. Teacher Oswald, we can't hear you.
Sorry about that. I think it was my network. So I was here explaining what allotropes are. And we said that carbon has got 3, but the main two are crystalline. So normally they ask us in an exam that they might ask us this question: name the 2 main crystalline allotropes of carbon. So if that question comes, there are only 2. That would be diamond. To be diamond and graphite. Then lastly, amorphous carbon. This is non-crystalline. Non-crystalline. So the other 2, diamond and graphite, are crystalline. Then the third one, which is amorphous, it is non-crystalline. I hope, Martha, you are now hearing me. Am I clear? Mr. Kakuru, am I clear that side?
Yes, we can hear you.
Okay. So we move on. I hope now we can differentiate between the crystalline allotropes of carbon and also the non-crystalline. So let's start with diamond. Let's look at diamonds as a separate allotrope. Anybody who knows anything about diamond can share with us. Diamond, you can maybe talk about its structure, you can talk about its properties, you can talk about anything you know about diamond in terms of chemistry. Anybody? If you know anything about diamond, please share with us. Okay, as we wait for answers, let's be moving on. We've got something here. Someone here says, that is Martha, says it is made of a single element. And what's that single element? What is that single element? What is that single element? Carbon. Okay, thank you. So she's saying that it is made up of a single element, and that is purely carbon. So let's move on slowly. So we say in diamond, the structure consists of infinite number of carbon atoms. Miracle says carbon is hard. Okay, thank you, Miracle. Carbon is hard. By this time we are, I think you mean diamonds, or carbon in the form of diamonds, which is hard. Okay, we move on. So we are saying infinite. When we say infinite here, we mean that these are very many. We can say very, very many number. In diamond, the structure consists of very many carbon atoms. So we can say very many atoms. That is how we can simplify this. Then each of the carbon atoms is joined to 4 other carbon atoms by covalent bonds resulting in tetrahedral arrangement. Miracle once again says diamond is hard and with high melting point. Okay, thank you. So this is what you've given us is one of the properties. Okay, thank you. So once again, I say that each of the carbon atoms is joined to 4 other carbon atoms by a covalent bond or covalent bonds resulting into a tetrahedral arrangement. Anybody who can share with us what a covalent bond is? Who can define for us a covalent bond? Who can define for us a covalent bond? So that we can be able to understand when we talk of a covalent bond, which is found in the diamond structure. What is a covalent bond? If you have done bonding, then you should be able to define this. What is a covalent bond? Because here we are saying that the carbon atoms are joined by covalent bonds. So we are trying to know what a covalent bond is. I'm waiting for the answer. So basically, a covalent bond, that's the bond formed. A bond formed between 2 or more nanometers. Between 2 or more nanometers. Okay, once again, Martha says it deals with sharing of different elements and atoms. Okay, thanks for trying. So here I think Martha, you meant to say that it is formed. It is formed by sharing of electrons. This bonding is covered under bonding and structure as a topic. But basically, covalent bond is between nanometers only. And like Martha said, it is also formed by sharing of electrons. At times we call it equal sharing of electrons. Then this gives diamond a crystal. Let's first remove this. So this gives diamond a giant 3-dimensional structure. When we say 3-dimensional structure, that is a 3D structure. So whenever they ask you to explain the structure of diamond, first of all, you have to talk about the very many atoms of carbon that are made up of that structure. And again, you have to talk about that each carbon atom is surrounded by 4 other carbon atoms. So here we are having, this is our main carbon. Maybe I can change the color here. You can make it maybe blue. Then it is surrounded by 4 other carbon atoms like this. So this is our carbon surrounded by other 4 carbon atoms. That is what we mean here, where we say that each of the carbon atoms is surrounded or joined to 4 other carbon atoms. I hope it is clear. Any questions there? If there was any question, we can repeat it. Then finally, the structure is a 3D structure. So that is the structure of carbon. This is the structure of carbon. That is how it looks. Whereby each black okay. Martha is saying that she didn't get point 2 and 3. Let me go back briefly. So here we said here we are saying that on point number 2, each of the carbon atoms is joined to 4 other carbon atoms by covalent bonds, resulting into a tetrahedral arrangement. When you talk of tetrahedral arrangement, this is what results into when you have a carbon atom, or it can be any other element, being surrounded by 4 other carbon atoms, or they can be any other elements. But in this case, we're talking about carbon. So here we have carbon, here we have carbon, also we have carbon. And each line you are seeing here, each line here, it is what we call a bond. If you have done bonding, each line you see is what we call a bond. So we are saying that carbon has got very many carbon atoms. Diamond has got very many carbon atoms. So this one, they keep on joining each other like this. So you find when they are very many, it keeps on expanding until it becomes very big. This is what we mean by being joined to 4 other carbon atoms, and also what we mean by saying infinite number of carbon atoms. They are very many in number. And then when they do that, when they join to each other, then they form a tetrahedral arrangement. Then, lastly, this gives diamond a crystal. So as it joins with other carbon atoms, 4 of them, as it joins, then form what we call a crystal. We form what we call a crystal. That is after joining several times. We shall cover most of these things when we go to the structures. That's when we have all the details. But apparently, diamond forms a crystal, or what we call a 3D crystal, or a giant 3D structure. When you talk of a giant, the giant from English, this is something very big. Something very big, so it keeps on expanding until when it becomes so big. I hope Martha will try to explain. Let's move to another slide. So this is where I was saying that here we have carbon, the black, all these ones are black, these ones, all of them, all these are carbon atoms. All these are carbon atoms. All these are carbon atoms. Then the blue ones. These blue ones are the ones we call a covalent bond. Covalent bond. So for example, if I pick this, it is joined by other 4 carbon atoms. It has this one as a number 1, it has this one as number 2, this one as number 3, this one as number 4. And even though if I picked this one, it will be having this one as number 1, number 2, number 3, then this one number 4. All of them are joined by these covalent bonds. And this is just a small part of it. For it keeps on expanding and expanding and expanding. And this structure is normally asked in an exam whereby you need to write it. If you look at its structure, it is like this. Then here we have carbon. Then we have this line here. We also have this line at some angle. And also this line for the covalent bond. So this is what we call a tetrahedral structure. A tetrahedral structure. Let's move on. Properties of diamond. Here we shall be a bit faster. So one, we have diamond, the hardest natural substance known. Like someone said, diamond is hard. And at times they can ask us the use and the application. If we say diamond is hard, then what is it used for? Anybody can tell us? We are saying that diamond is hard. Being hard, how do we apply it or how do we use it? We shall find that since diamond is hard, it is used to make what we call rock borers. Rock borers, at times they call them drillers. Then it also has a very high melting point because of the strong covalent bonds. The bonds we saw. If I sample out, these bonds, they are the ones we call strong covalent bonds. And also, of course, of being big, we say it is giant. So even its size gives it a high melting point. Then it also has a density of 3.5. This is a big density, 3.5 grams per cubic centimeter. Diamond is transparent, sparkling, and glitters. If you ever see like rings of diamond, all of them are transparent. In other words, you can see through. They are sparkling and also glitters. So at times they can ask you, why do we use diamonds to make, for example, jewelry? Why do we use diamond to make jewelry? It is because of being sparkling and glittering. It is able to do that. Why do we use diamond to make drillers or rock drillers or glass cutters? It is because we have said it is very, very hard. Diamond does not conduct electricity. Diamond does not conduct electricity because it doesn't have mobile electrons. When we talk of mobile electrons, these are the ones that are used by substances that do conduct electricity. Any questions on diamond? Any questions on diamond? Okay, as we wait for questions, if there is any. Let's look at the uses. These uses normally are in accordance with the properties, like I said. Normally, we give the uses in accordance with the properties. You can't say it is used to make maybe a soft substance, yet we say it is hard. So you have to give a use in accordance to the properties. So diamond, we say it is very hard, therefore it is used for making and reading the devices, or what we call rock borers and also glass cutters. So here we are having a use depending on the property, where we say it is the hardest substance known. Diamond is used in jewelry because of sparkling appearance. So we said it sparkles, and at times we can use the word glittering. Diamond is bright. Remember here we can say, we say it is because of being transparent. So it is used to make laser beams. It is used to make laser beams. So once again, members, here we are just giving a few examples, few uses because of time. So we can add on later on after the lesson. You can add on other uses that you know. I'm not saying that they are only 3; they are more than that. Any questions so far? We are now moving to another outro. We are now moving to another outro. Okay, it seems there are no questions, but in case you get any, feel free to ask. So let's go to the second outro that we call graphite. Graphite consists also of many number of carbon atoms, each covalently bonded to the 3 other carbon atoms in the hexagonal rings that are arranged in layers. So can someone now tell me the difference between the graphite when it comes to arrangement of carbon atoms? Anybody who is seeing the difference between the arrangement of carbon atoms in diamond and also the arrangement of carbon atoms in graphite? However much all of them are having very many carbon atoms. Anybody to point out the differences? Anybody to point out the differences? Anybody to point out the differences according to what we discussed about diamonds? Okay, as I wait for differences, I can also be identifying some. So we said for the case of diamond, we say that each carbon atom is bonded to 4 other carbon atoms. But here we are saying it is bonded each carbon atom. Okay, an answer has come. Mother say, I think because it has an infinite number of carbon atoms, it is soft. Okay, thank you for trying. Any other person to try? Miracle says, in diamond, each carbon atom is joined to 4 others. Why in graphite to 3? Okay, thank you. So we say that in carbon, in diamond, there are 4. But now in graphite, we are saying there are 3. How about the rings or what is being formed? In diamonds, we are forming a tetrahedral structure. Tetrahedral structure. Okay, Mirav has said it. Diamond has tetrahedral structure, whereas graphite has hexagonal structure. So diamond has tetrahedral, then graphite has hexagonal rings that are arranged in layers. But remember, in diamond, we didn't have anything to do with the layers. Then each layer is a giant two-dimensional structure. Once again, Miracle says diamond forms giant structure, whereas graphite is in layers. Thank you. We are now on point 2. What is the difference between that of diamond and this one of graphite? What did we say about dimensional structure of diamond? You can tell us very fast, very fast. We said diamond has what? Diamond has, okay. Diamond is tetrahedral, that's fine. But there's how we talked about something like dimensional structure. Here we are saying that each layer is a giant two-dimensional structure. How about for diamond? What do we say? It is how? It is, what is the dimensional structure there? Okay, thank you. Thank you, Miracle. So for diamond, it's 3D. But for graphite, it is 2D. So here we are trying to get the differences earlier so that we don't go there. The difference between diamond and graphite. So we said that the different layers are held by weak van der Waals forces of attraction. The weak layers are held by weak van der Waals forces of attraction. Now we have brought in a new term, which we call van der Waals forces of attraction. So when we say van der Waals forces of attraction, Ibrahim says it is opaque and shiny. Okay, thank you, Ibrahim. So here we are talking of weak van der Waals forces of attraction. Here I can say these are very, very weak forces of attraction, very weak forces of attraction. So for them, they are by names of weak van der Waals forces of attraction, whereby van der Waals is the person who discovered those forces. So they were named after his name, making them slide over each other. Thus, they are slippery and soft. In other words, graphite, yeah, we mean that graphite is soft and slippery. Okay. At time they can also ask you explain. They can ask you to explain why graphite is soft. Why graphite is soft. So you have to come and explain this. You have to come and say that different layers in graphite are held by weak van der Waals forces of attraction, which make them slide over each other. That is how we can explain why graphite is soft and slippery, if the question comes like that. So that is the structure of graphite. Here, this is some, I think this is a bit better. Then here we are giving the details. Here we are giving the details. So each black spot, it goes for carbon. So wherever you see a black spot, it will be carbon. And we say that each carbon atom is bonded to 3 other carbon atoms. For example, if I pick this one, it is bonded to this one, to this, and that. Then this is the first layer, as you can see. Upper layer of hexagonal rings, lower layer of hexagonal rings. So these two lines we are having, these ones here, These are the ones we call weak van der Waals forces of attraction. So we are trying to show how the forces between the first layer and the second layer look like. And also again to show that graphite is made of layers which slide over each other. And once again, you can be required to draw this kind of structure. You can be required to draw this structure. But what we should know is that each carbon atom is bonded to other 3 carbon atoms. And the carbon atoms, for them, they are connected or joined by covalent bonds, like the way we have it here. It is the layers, because they are the layers which are connected by weak van der Waals forces of attraction. We shouldn't confuse that too. Carbon to carbon, it is covalent. Layer to layer, it is weak van der Waals forces of attraction. I hope it is clear. If there are questions concerning that, please feel free to ask. So let's move on. Properties. Some of we have already talked about them. Graphite conducts electricity because it has free and mobile electrons. So I think I can also ask, why does graphite conduct electricity? Because of having free and mobile electrons. So they are able to move from one point to another as they conduct or transmit electricity. So if this was our graphite and this is a source of electricity, it is going to do this. Each electron is going to carry electricity from one point to another. Then eventually, it will be transferred from one point to another. This is point 1, point 2. So in other words, the electrons in graphite are able to move from one point to another, which is not the case with diamond. The melting point of graphite, it is high because of the strong covalent bonds. Graphite is soft, we've talked about it, and slippery because of the layers held by weak van der Waals forces of attraction. The graphite is opaque, Miracle talked about it, it is opaque and dark. Remember, for diamond, we say it is transparent. I hope transparent is the opposite of the word opaque. Then also say it is transparent. This one we say it is bright, or where we say it is sparkling. When we say opaque, it means that we can't see through. So if it is the graphite, we can't see through. So it is opaque, dark in color, and shiny. Let's look at the uses. Graphite is soft and can mark, therefore used to make pencil leads. So we can use graphite to make pencil leads. If you have your pencil, it has that black substance in between, the one you used to write. It is made of graphite. Then when it makes this grade, also used to make pencil leads. It is a good conductor of electricity. Who can remind us of the reason why it conducts electricity? Who can remind us of that reason? What do we say? Why does graphite conduct electricity? Why does graphite conduct electricity? Who can remind us? Why does graphite conduct electricity? Why does graphite conduct electricity? Who can remind us of that reason? We talked about it. I'm waiting. Who can remind us why graphite conducts electricity? Anybody else remembers? Why does graphite conduct electricity? Miracle, do you still remember? Okay, we've got an answer in the chat. Okay, Martha said it's because of having free and mobile electrons. Thank you. And Ibrahim also says it is because of having free and mobile electrons. Thank you so much. So that is the reason. It is because of having free and mobile electrons. We have another answer. Miracle says graphite conducts electricity because its atoms are joined by 3 covalent bonds, yet its valency is 4. This leaves a free electron which is free to move about. Okay, thank you. So she's saying that carbon has a 4, a valency of 4, but remember we are having this carbon graphite only joined by 3 carbon atoms. So we have a free electron here, which is not used. So it's the one that moves around. And since we have very many carbon atoms, then they will give us many electrons, which are able to move from one point to another. Thank you for your answers. Then again, we are saying it is soft and greasy and therefore used as a lubricant, especially in small bearings like those in diamonds and dynamos. So why do we say it is soft? What's the reason? Why do we say that graphite is soft? Why is graphite soft? What do you think? We talked about it. So what do we say? You can tell us why is diamond soft? Rather, why is graphite soft? Why is graphite soft? What do we say? If you remember, there is where we said soft and slippery. It is the same explanation. Like I said, under diamond, each use is connected to a property. So can tell us why is graphite soft? Okay. Mother says the layers are held by weak van der Waals force of attraction. Thank you. And Miracle again says graphite is soft because its layers are joined by weak van der Waals forces of attraction. Thank you so much. So that is it. It is because the layers are held by the weak van der Waals forces of attraction, whereby they are able to slide over each other. We move on. Graphite is used to make brushes for electric motors. Why do we say it is used to make brushes for electric motors? Who can guess the property that we are applying here? Who can guess the property that we are applying here? Remember, we are having this word here, electric. So for me, I think it has something to do with electricity. It is because of why do we use it to make brushes for electric motors? It is because of, okay, we have got the answer. It is because of having mobile electrons. Thank you, Martha. So finally, graphite is black and is used as a protective coating in iron to prevent rusting. It is black and is used as a protective coating on iron to prevent rusting. Okay. Any questions concerning graphite? Any questions concerning graphite? Any questions concerning graphite? Let's move on. Once again, if you have any questions, please feel free to use the chat box, or you can be allowed to ask. So let's look at the last one, the last isotope of carbon. Remember the other ones we said they are crystalline, and this one we said. But still remember, what's the nature of amorphous carbon? Is it crystalline or non-crystalline? Is amorphous carbon crystalline or non-crystalline? Who can remind us? Who can remind us, is amorphous carbon crystalline or non-crystalline? Okay, Martha says it is non-crystalline. Thank you. Also, Joanne says it is non-crystalline. Thank you, Joanne. All right. So to remind ourselves still, we are saying that this is non-crystalline. Miracle say graphite is used to make brake pads. If yes, why yet is it slippery? We are saying that it's slippery because of the layers, of having the layers which slide over each other. But the brake pads now we are using the other option of the carbon atoms being held by strong covalent bonds. So because of the carbon atoms being held by strong covalent bonds, then it can be used to make the brake pads. So once again, amorphous carbon is non-crystalline, and we say the ones which are crystalline are diamond and graphite. These are crystalline. Let's look at this. Amorphous carbon is black and has the lowest density. It is black and has the lowest density. It is also non-crystalline and fair, it conducts electricity. And amorphous carbon exists in several forms. For example, we have wood charcoal. Wood charcoal is the same as the charcoal we use for cooking. We have animal charcoal. We have sugar charcoal. We have lamp black and also coke. So here, what I will request you have to go and make some research about this, especially the preparations. So because of time, we might not go through all these, but after this lesson, you can go and check how do we prepare or how do we form wood charcoal, how do we form animal charcoal, how do we form sugar charcoal, lamp black, and coke. So these are the examples of amorphous carbon. Please, you have wood charcoal, animal charcoal, sugar charcoal, lamp black, and coke. And normally, after asking the example, they also ask you how they are formed. So that's why it is important to go and find out how these are formed. Then from there we go to the proof that show that graphite and diamond are atoms of carbon. So we want to show, why do we say that diamonds and graphite are made of carbon? So we want to find out, how do we prove that? So what we shall do, we shall get 1 gram of both diamond and graphite. In other words, we get equal masses. Some books say equal masses. We shall get equal masses of diamond and graphite. Then we burn them in oxygen. When we do so, we shall form carbon dioxide. In other words, if I burn one gram of graphite, if I burn 1 gram of graphite, let's say if I get 10 cubic centimeters, if I get 10 cubic centimeters of carbon dioxide, I'm supposed to also get 10 cubic centimeters if I burn the same mass of diamond. So if that happens, we say that diamond and graphite are atoms of carbon, and we are forming only one product, and that is carbon. Rather, that is carbon dioxide. So if I have graphite, which is in the form of carbon, I burn it in oxygen, then I will form carbon dioxide gas. So this is the reaction that takes place. Carbon here, it can be graphite or it can be diamond. Once burnt in oxygen, then we shall form carbon dioxide. Certainly they can ask us to prove that, so that's what you do. If you don't want to use the 1 gram, Then you can say when equal masses of both diamond and graphite are bound in oxygen, they form the same amount of carbon dioxide only. So this shows that they are atoms of carbon. Okay, so as we wind up, oxides of carbon, let's start with carbon dioxide. So carbon dioxide, the chemical formula is CO2. Carbon dioxide occurs in air and it occupies 0.03% by volume of air. Carbon dioxide form is also found in rocks as a result of volcanic eruptions. It also occurs in mines as chalk dump, and is also present in natural drinking water because it's slightly soluble in it. Look at preparation. So we have the diagram for preparation. This is what we call laboratory preparation. It's what we can do in the lab. What we need, we shall need dilute hydrochloric acid. The acid must be dilute. There is sulfuric acid, hydrochloric acid. Then we need calcium carbonate. Calcium carbonate, or you can use any carbonate. It can be calcium carbonate, it can be sodium carbonate, any carbonate as long as you have dilute acid, which is hydrochloric acid. Or at times we can use sulfuric acid, but we shall look at the disadvantages of using sulfuric acid. So after that, we put in the flask, we add there the acids. Then we shall produce carbon dioxide, which is collected over water. Why are we saying it is collected over water? Carbon dioxide is collected over water because it is slightly soluble in water. So what we mean here is that a small portion of it can dissolve in water. If we talk of 100% of carbon dioxide, we can say only 0.01% can dissolve in water. So it's a small percentage that dissolves in water. Otherwise, if it was soluble, very soluble in water, then we wouldn't be collecting it here. It will all dissolve in the water and we end up not having carbon dioxide. So the one we have prepared here, this is not a pure sample because it contains some impurities. So this is just for normal preparation. So the procedures arranging the apparatus are shown above. That is drawing the diagram we have above. Then we add there hydrochloric acid in the flask to the funnel. Then what do we see or what do we observe? We shall see effervescence occurs as a Carris gas is given off. So we shall see a Carris gas being given off. Then the equation or the reaction. Here we are having calcium. So we have calcium carbonate, which is a solid. And then we add there hydrochloric acid. Then we shall form calcium chloride, which is aqueous. Then carbon dioxide gas. Then finally, water. Then we balance. At this side, we are having 2 chlorine atoms. We have these 2. So we need to even this side. So that's why we put the 2. That's why there is this 2 here. Then after that, we check again. Calcium, we have 1. This side we have 1. Carbon, we have also 1. This side also have 1. Oxygen, we are having 3. This side we are having how many? We have 2 plus this 1, which give us 3. So they're also balanced. Hydrogen, here we have 2. Then this side also have 2, it is balanced. And then for chlorine, it is also 2. It is 2 times this 2, then times this 1 here. So chlorine we have 2, and also here we have 2. So we find that the left-hand side is equal to the right-hand side. That is what we call a balanced equation. If you add up all the atoms on the left, it should be equal to all the atoms on the right. Let's check. Here we have 1 plus 1, that is 2, plus 3. That is 5 plus 2, that is 7 plus 2, 9. So on the left we have 9. On the right, that is after the arrow. The moment you cross the arrow, then you go to the right hand side. We have 1 plus 2, that is 3, plus 1, 4 plus 2, plus 2, then we get 6, then plus this 3, we get 9. So we say the equation is balanced. We shall have another lesson about balancing equations. So this gas may be collected over water, like we said in the diagram, as it is only slightly soluble in water. So we said the gas is collected over water because it's slightly soluble in water. So if the gas is quite dry, then we do this. If you want the gas to be dry, if a pure dry sample of carbon dioxide is required, the gas is first passed through a drying agent. It is passed through a wash bottle containing concentrated solution of potassium hydrogen carbonate to remove traces of hydrogen chloride gas. So this chloride gas, this one is produced by hydrochloric acid, which is not the case. The diagram we have does not have the removal of the hydrogen chloride gas. So that's why I say that this one, whatever we prepare here, it is impure. It has impurities like hydrogen chloride gas and also water as an impurity. Then from there, it is passed through a U-tube containing fused calcium chloride to dry the gas. So here we remove water. Here we are removing hydrogen chloride gas. Then after that, the gas is collected by downward delivery method, since it is denser than air. So we have a diagram. So the diagram we are having here is different from what we had before. Here we are having dilute hydrochloric acid. We are having calcium carbonate, which is the same the other side. But now we are having a wash bottle or a container having potassium hydrogen carbonate. What is the use? The use is to remove traces of hydrogen chloride gas, which are produced by this acid here, hydrochloric acid. Then from there, it is passed through a U-tube. It is passed through a U-tube. So this is what we call the U-tube, which contains a drying agent, calcium oxide. So the drying agent can be calcium oxide, it can be calcium chloride, or it can be concentrated sulfuric acid. All these are different drying agents. Then once the gas is dried, then it is collected by downward delivery. And we are saying it is because the gas is denser than air. In other words, when the gas is being collected, it goes downwards. It goes downwards like that. Any questions so far? Any questions? I'm sure I'm a bit faster. I'm trying to find time. Any questions? Okay, it seems there are no questions. So yeah, I'm showing you the same diagram, but on a big space. So this is what we have just seen. We say this is a U-tube. And this is we say it is by downward delivery and so on. Okay. So I want us now to go through the questions very fast. I had prepared some questions. So you need to look at the questions very fast. So that means that you need to get your summary book where you've been writing. I'm getting the copy of the questions. Mr. Nakuru,
Yes.
I'm unable to share my screen.
Yes.
I'm trying to share my screen, but it's not being shared.
Okay, let me make you a co-host.
So members, we're just going to go through the questions very fast.
Are you able to share now?
Let me say, not yet. I'm not able to share.
Which message do you get?
No, it is not clickable.
Try again.
It's not. Maybe let me log out and come in again.
Okay.
Okay, I'm back. Therefore, you can now make me the host. Okay.
Yes.
It's now fine. So I hope everyone is able to see my screen. Let's go through these questions very fast. We see the ones we can answer and the ones we cannot. So we start with I hope everyone now can be able to read. So there are some questions that so far we have covered. Anybody define for us allotrope and allotropy? You can use the chat box or you can unmute yourself. We are just reminding ourselves of what we have just so far covered. Martha, can you help us?
Yeah, allotrops are various forms in which elements exist without a change in physical state. And allotropy is the existence of an element in two or more forms in the same physical state.
Okay, thank you, Martha. Thank you, Martha. Let's go to part B, Roman 1. Name two crystalline forms of allotropes of carbon. What did we say? We said there are two, namely Miracle. John, I see your microphone is open. Do you want to give us an answer? So what are those crystalline atoms of carbon? What do we say? We have okay, Martha says that Martha says graphite and diamonds, and even Ibrahim says graphite and diamonds. So we had diamonds and graphite. Thank you. We go to part 2. Outline 3 differences between the two allotropes. In other words, we want the difference between diamond and graphite. You can give us 3, only 3. You can unmute and give us only 3 difference between the two allotropes, diamond and graphite. Use the chat box, or you can unmute yourself and give us the answers. The difference between diamond and graphite. We talked about them. What should I start with? Miracle, let me start with you. Miracle, you can give us 1 difference or 2. Okay. John says diamond is hard while graphite is soft. Thank you. Martha says diamond is hard while graphite is soft. Thank you. Diamond is also transparent, and while graphite is opaque. Okay, so those are 2. Those are 2. The first one is repeated. So we have diamond being hard and graphite being soft, and also diamond being transparent and graphite being opaque. Ibrahim says diamond is very hard and also used for drilling, to make drilling devices. Okay, thank you, Ibrahim. But it's the same as displaying the first property. So can we have the third property? We can talk about the structure. What do we say about the structure of diamond and the structure of graphite? We say that diamond has what? Or graphite has what? So Mother says that diamond does not conduct electricity while graphite consists of electricity. I think you are supposed to write conducts electricity. So diamond does not conduct electricity while graphite does not conduct, while graphite conducts electricity. And we say that graphite conducts electricity because it contains free and mobile electrons, whereas diamond does not contain those free and mobile electrons. Okay, let's move to the third part. How do you prove that the allotropes consist solely of carbon? So how did you prove this? What do we do? We are here. We are here. How do you prove that the allotropes consist solely of carbon? You can unmute and give us an answer. Okay, there we said that we get equal amounts of carbon or equal amounts of graphite and diamond. Then we burn them in oxygen, they will give us the same volume or the same amount of carbon dioxide. So members, because of time, we shall not be able to go through all these questions. There are very many, there are 6 of them. But once you look through the work, I'm going to share with you the presentation, and then you go ahead and read, and you're able to attempt these questions. Why, if you understand, you reach me. You can reach me via my WhatsApp number, or you can call me. Then I'll be able to help you. So if you have any other questions, you can ask as we wind up. Okay, it seems there are no questions. So I want to thank everyone for attending. I want to thank Yaka for this program and everyone who is supporting us. Mr. Kaku, thank you, and your team. Okay, I'm going to share my number. I'm going to share my number in the chat. (0705) 900 414. MTN 0780 802511.
Hello, Oswald, can you hear me?
Yes, I can.
Yes, it has started raining on my end, and the voice may not be all that clear. We thank everyone who has attended today's seminar. We have more seminars coming up. Let's continue to sign up for them and enjoy the best from Yaka Digital Network. Have a blessed afternoon. We can keep the questions coming in the chat section. I will be answering them. Thank you.
Thank you, Mr. Kakur. So everyone I wish you a nice day and a nice weekend.